Alright gang, here we go. This is Chem 2 Unit 5. We're talking about how to tell whether or not your molecule is polar. So in the previous video we talked about how to determine the VSEPR structure, the three-dimensional structure of your molecule. And we talked about, our different ways we can attach things to our central atoms, what their bond angles would be, so on and so forth. And now we're going to talk about polarity. Now polarity is important because this gives us a clue as to how it's going to interact with other things. When we get to our unit about intermolecular forces, this is going to play a big part. So it's important to become pretty good at this stuff now so that later you don't have to worry about it as much. All right. So when you're finding out whether or not a molecule is polar, okay, now remember we talked about, just take one step back again, sorry. We talked about whether or not to see whether or not a bond was polar, right? So this is, we used electronegativity, right? For bond polarity. Now, remember, bond polarity is just between two specific atoms, right? And we're just saying, okay, is the electron density more on one side of the atom, or more on one atom, or more on another atom, or are they shared equally? In a molecule, though, we're looking at the whole thing, this whole thing, multiple atoms that are put together, and we're essentially asking ourselves the same question: are the electrons being shared equally across the whole molecule, or are they going to be more concentrated on one side versus the other? Okay, so the first thing we have to ask ourselves is our molecule covalent or ionic? Excuse me, I had to sneeze. All right, so we ask ourselves, is our molecule covalent or ionic? Well, if it's ionic, then we don't have to worry about polarity at all. It's automatically polar because ionic compounds, they give up their electrons, so the electrons are going to be more on the more electronegative atom, period. Full stop, done. All right, but if it's covalent, there are several things that we have to do. The first thing that we're going to do is we're going to draw a Lewis structure. All right. So drawing a Lewis structure is absolutely the first thing that we got to do. Okay. Now, from there, we determine the geometry. Okay. Geometry. Okay. And then, really, we're going to ask ourselves a series of questions. Now, the way the book kind of gives this to you is it's kind of like a straight shot, binary. The problem is that this is kind of where chemistry becomes more of an art and less of a science, in that there's a lot of things at play. And so you kind of have to think about the whole picture as opposed to just yes or no binary, kind of experience. So it's a little bit tricky to kind of get used to it. For example, they say the first step to ask yourselves here is, are the bonds polar, or do they have a bond dipole? And they say no, if the bonds are not polar, then the molecule is nonpolar. Now, this isn't really true. This is true in a lot of cases, but there are examples of molecules that are polar even though their bonds themselves are actually nonpolar. Okay. And then they say the next step, so if it is polar, they say, do the average positions of the partials and positive and negatives coincide? Or essentially, do you have an overall dipole moment equal to 0? Now that's really what the whole question is. So this is kind of a redundant question. So I'm really not a fan of this slide that I put together, because this question here is the overall dipole moment equal to 0. That's what you're asking yourself to begin with. Okay, like if your dipole moment is 0, then that's saying that you're nonpolar, and if your dipole moment is non-zero, then that means you're polar. So really, they're saying, okay, a step to asking yourself if it's polar is just asking yourself if it's polar, and this is kind of bonkers. So anyway, so here's the steps I go through: draw Lewis structures, add geometry, and then really you're looking for symmetry. Okay. All right, and that's really the key that you're asking yourselves. Okay, like the general principle is that if a molecule is symmetric, all right, if it's symmetric, that means then that means your electrons are shared equally, and then that means you're nonpolar. Okay. All right, and then if it's non-symmetric, then that means that your electrons are not shared equally, so that means you're polar. And that's really like this is really how I go about answering these questions. Is it symmetric or is it non-symmetric kind of experience? Okay. So here's just two different molecules. So carbon dioxide here is like the quintessential example of a molecule that has polar bonds, but is nonpolar overall. Okay, carbon and oxygen have an electronegativity difference of 1, 3.5 to 2.5, so that gives you your polar bond, but because it's linear and one dipole is pointing directly left and the other one is pointing directly right, they cancel each other out, and so the overall dipole moment is 0. And you can see based on this electronegativity, or this electron density graph, you can see that in the middle there's low electron density, but as you go to the left and to the right, you get the symmetrical distribution of electrons. And then, but on the other side, you get water, who has their bond dipoles are pointed in the same directions. They're both going up generally, right? One's going to the right, one's going to the left, but they're both going up. So its overall dipole moment is up. See how you can kind of combine this this one here and this one here to get this overall dipole moment, because the left and right components of these lines will cancel, and you'll end up with just going up. All right, and then we can see that with our electron density as well. On the oxygen side of the water molecule, we got a whole bunch of electrons, and then on the hydrogen side, we got a whole few, or less electrons, low electron density. So here's a couple of graphs to help us kind of picture what's going on. So, or a couple of comics to help us visualize what's going on. You got a penguin, okay, and he's hydrogen, and then polar bear is chlorine, and they're sharing an ice cream cone. Now chlorine is a lot stronger than penguin, so this is saying that chlorine has a lot more electronegativity, and so here's the bonded pair of electrons they're sharing, and the chlorine is going to pretty much hog this thing. And then you get the same kind of idea. Here's carbon dioxide. Now the penguin is carbon, and the polar bears are oxygen. Notice that there's 4 scoops to represent the 4 electrons that are shared on either side, the double bonds. It's pretty funny. I like that. All right, so we're going to do a couple practice problems here, and then we'll be done. Okay, it's consider an AB3 molecule in which A and B differ in electronegativity. You're told that the molecule has an overall dipole moment of 0. So this tells us that it's nonpolar. All right, it tells us it's nonpolar. It says, which of the following could which of the following could be the molecular geometry of the molecule? All right, so A, so trigonal pyramidal. Well, that would look something like this. We got A, so trigonal pyramidal is based off tetrahedral, so that means we've got a lone pair on this guy, and then that means we'd have a B coming off this way, and then we've got a B coming out of the page at us this way, and then a B going back into the page like this, remember? So trigonal pyramidal is kind of like that tripod thing. It sits there. And so this guy here, because of this lone pair, you can kind of imagine that you'd like, they've got a difference in electronegativity, but because there's no symmetry between the top and the bottom, this side, this would be polar because it's non-symmetrical. You got this lone pair up here. It's kind of pushing all these guys down. And another thing to think about, just bond angles, just keep practicing those. So this is tetrahedral, so it's based on 109.5, but these lone pairs take up more space, so they're going to push everything down. So the bond angles between the B bonds, AB bonds, between these 3 would be less than 109.5. All right. Trigonal planar, though, so that means trigonal planar is its own thing. That's where you've got 3 electron domains. So you got A to B, A to B, and A to B. Okay. And so because your electron density, you've got, this is completely symmetrical wherever you draw it, because we can draw it this way and it's symmetrical, we know that this guy is nonpolar. All right, so far B is the right answer, trigonal planar. All right, but it could be one of these other two because this is more than one of the above. So really we have to check all of them to answer this question. All right, C is T-shaped. Well, T-shaped is based off of trigonal bipyramidal. So we've got A. Let's see, how would we draw this here? We'd say A, B, B, and B, okay? And then we've got 2 lone pairs. One lone pair is going back. Lone pair, I really don't like it, doing it like this, but it is what I chose to do. So there's your trigonal, or sorry, your T-shaped. All right, so this guy, because it's non-symmetrical in this direction, we can say that this guy is polar. All right, so A and C are right out, okay, and then we got to check D. Well, D is tetrahedral, which means it has to have from 4. It would have to be AB4, so this isn't even possible. It's not even possible to be AB3, so we don't even have to check that. And so it had to be B, it would be trigonal planar. All right, determine which of the following molecules are polar or nonpolar. All right, so SF4, okay. So sulfur and 4 fluorines. We're going to add those guys up. Sulfur has 6, Fluorine has 7, so 4 times 7 is 28. Plus 6 is 34 electrons. Yeah, 34 electrons. All right, so sulfur is going to go in the middle because it's the least electronegative, so we'll put sulfur. And then we'll go 1, 2, 3, 4 for our 4 fluorines that are attached. We'll add lone pairs to everything. All right, count up the electrons we've used. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We need to use 34. That means our extra 2 electrons are going to be on here. All right. So that means that the structure of our molecule would actually be, so it's 5 electron domains. 4 of them are bonding, 1 of them is lone pair. So this would be a seesaw molecule. So remember, seesaw molecules kind of look like this. So we'd have S, and then F, F, and we'd have one F coming out here, like this, and we have one F coming out back into the screen like this, and then we'd have the lone pair sitting up top like this, kind of doing this kind of number. And so you can kind of easily see that you're non-symmetrical, that even though this fluorine-sulfur bonds are polar, you've also got this electron density right here, so you got kind of a region of non-symmetricalness here. So this guy would be polar, so A is polar. All right, A is polar. Now let's try B here. All right, so silicon tetrachloride. All right, so you got silicon and 4 chlorines. We're going to add those guys up. Silicon has, silicon has 4 valence electrons. I should have known that. It's right underneath carbon. That was silly. And then 4 times 7, so it's got 32 electrons. All right, so then we put silicon in the middle, attach all these chlorines to it. All right, give it full lone pairs. And if you were paying attention from the last problem, you know that we had essentially the same setup with the sulfur, and we had 32 electrons here. So we can just count them up just to double check. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So this is this shape of this guy. So this guy's tetrahedral. All right, and because all of these bonds are the same, okay, for SiCl4, if the Si was attached to like HCl3, like so instead of one of those chlorines being an H instead of a Cl, then it would be polar. But because it's all the same, it's completely symmetrical, then no matter how you cut it, then this would be a polar or non-polar molecule. All right, and so that's it. Next video we'll talk about valence bond theory, but for now just practice knowing whether or not you have a polar molecule. Do your homework. Let me know if you have any questions. I'll see you on the flip side.